Let's prove that the limit as theta approaches 0 of the sine of theta divided by theta is equal to 1. We'll do this by the squeeze theorem. So again, let's consider our setup. We're on a unit circle. We'll look in the first quadrant. The unit circle, then we will extend some angle into the first quadrant. We will call this angle theta. Okay. When theta is measured in radians, the length of this arc will also be equal to theta. We can drop an altitude here, and we know the length of that altitude should be the sine of theta. Now, there's another triangle that we can draw, and it comes up here, and we can extend this to meet. Okay, so now we have a new triangle. Okay, now the base of this triangle is here, and we could write, we know that the tangent of theta will always be equal to, in a right triangle, the opposite over the adjacent. Okay, so this would be the adjacent side, but remember we are on a unit circle, so that length would just be 1. So we can say for this triangle that the tangent of theta is equal to the opposite over 1, which is just the opposite side. Therefore, the length of this triangle's side is the tangent of theta. So if we are in the first quadrant, that is for theta that is greater than 0 and less than pi over 2, we'll be in quadrant 1. We have then that the sine of theta must be less than the length of that arc, theta, and that must be less than the tangent of theta. Okay, so this is the inequality that we're going to manipulate and use for the squeeze theorem. All right. Now what we want, okay, so what we have, let me just rewrite this, is the sine of theta less than theta is less than the tangent of theta. Okay, and what we want, because we're trying to prove something about the limit of the sine of theta over theta. Now I just don't want to go dividing by theta over here, because then theta, the sine of theta over theta won't be in the middle, and we won't be able to use the squeeze theorem. But we're still going to manipulate this. So let's divide everything by the sine of theta. And that's not quite what we want, but it will get us much closer. Then what we'll have, the inequality reads 1 is less than theta divided by the sine of theta. And the tangent divided by the sine is just 1 over the cosine. Okay, so this is our new inequality. And this is really close. We have theta divided by the sine of theta. What we want is the sine of theta divided by theta, which is fine. We can do that. We can just take the reciprocals of everything. So the reciprocal of 1 is 1. The reciprocal of 1 over the cosine is just the cosine of theta. But when you do this with inequalities, you have to make sure that you flip the inequality symbols. Okay, but that's all we need to do. So now let's apply the squeeze theorem. We're looking for the limit of as theta approaches 0, so we need to do it from the left and right hand sides. So we'll have the limit as theta approaches 0 from the right of 1 must be greater than the limit as theta approaches 0 on the right of the sine of theta over theta, and that must be greater than the limit as theta approaches 0 on the right of the cosine of theta. Now we can just take these limits. 1 is a constant. It does not depend on what's happening to theta, so this limit is 1. 1 must be greater than the limit as theta approaches 0 on the right of the sine of theta divided by theta. And in the last video, we showed that the limit as theta approaches 0 of the cosine is also equal to 1. And that's the result we need. Therefore, we'll come back up here. Therefore, by the squeeze theorem, we've shown that the limit as theta approaches 0 from the right of the sine of theta divided by theta is equal to 1. Now, by a similar argument, we can also show that for the left-hand side. So we can show that the limit as theta approaches 0 on the left of the sine of theta divided by theta is equal to 1. Then, since the left and right-hand limits exist and they agree, the full limit exists and is equal to 1. Of the sine of theta divided by theta is equal to 1. Therefore, okay. And that's it. That's what we